How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of freely falling bodies and bodies which are projected, projectile motion. And I would remind you of things already learned in earlier lessons, such as, for example, a body of small mass, a body of enormous mass, released to fall freely, released simultaneously to fall freely. And what is their behavior? They fall at the same rate. And you remember it is Newton's second law that tells us that, namely that F equals ma, or for freely falling bodies, W equals mg. Now, what is the action of a body falling freely? Of course, it encounters in real life some viscosity and friction and trouble with the atmosphere. So what we can do is lodge a heavy body and a light one, say a coin and a piece of paper, in a tube, and then with a vacuum pump, take out as much air as we can, and then do as follows, and we would see both bodies fall at the same rate. I had this tube originally evacuated, but there has been a leak, so the experiment, as some would say, has failed. But I remind you, I have not provided nature with her requirements to show the simultaneity of fall of both bodies in free space. Now, when we study a falling body, dropped so like that, we learn as follows. Supposing it starts right there. 1 second elapses, and we find it right there. How far has it fallen? 16 feet. Now we let another second elapse, and I'm not drawing this to scale. And how far would it fall in the second second? During the second second, it would fall 48 feet. Now let it fall for a third second. And how far would it fall during the third second? And we find 80 feet. And these numbers have some mathematical enchantment, because 16 divided by 16, 48 divided by 16, 80 divided by 16, and we see that the numbers are the odd numbers beginning with unity, which is a discovery that Galileo made in the 16th century. Now, further than that, you see that the first 2 seconds is 64 feet, the first second is 16 feet, the first 3 seconds is 144 feet, and look at these numbers. 16 into 64 is 4, that's 2 squared. 16 into 144 is 9, that's 3 squared. So the distances all fallen during the succeeding seconds are in the order 1, 4, 9. You see, 1, 4, 9. 1 squared, 2 squared, 3 squared. Now, when we study a freely falling body, it is too far to measure in real life. So what do? We have a machine which records a falling body and where it is every 60th of a second. And here is a tape which I have run, and the point to be noticed is that the distances as we go down increase in the order I have described, a discovery made by Galileo. Now, there is another exciting adventure regarding falling bodies. Another very exciting adventure. Supposing I had a body A and a body B on the same horizontal level with respect to the ground. And what am I going to do? I'm going to allow A to fall freely, and B, I'm going to project horizontally, like that. Now, you know the path it takes is a parabola. Indeed, this was discovered also by Galileo in the 16th century. And the question that's enchanting is this. How about their times of arrival at the ground? The impulsive notion is, well, this is going much farther and hence should take longer. But that is not true. The time of fall for A to the ground and B to the ground are one and the same. Why? Because the horizontal velocity of B remains unaltered, and the vertical velocity is taken care of by gravitational forces, the same in both cases. And here we have an experiment, a demonstration to show that. Here is a device with a spring which permits me to shoot a ball horizontally, as in the case of B, and here is one that I can release to fall freely, as A in the picture, and we will rely on our senses, hearing and sight, to verify what happens. Watch it. Simultaneity of impact. Now, this is not a proof, but it is a suggestion of the reliability of the law of falling bodies and projectiles. Consider now another one. This one has absolute enchantment. Let me put a ball in a car on a spring. And now I will put the spring in compression, drive the car away from me. The spring will be released and project the ball vertically, and the car will go horizontally, and it does no longer have the ball in it. Pretty soon the car is over here. And what do we discover? We discover an amazing and wonderful thing, that the ball is caught by the car. And I'm going to show you that. First, let us take a look at the mechanism. Here is the cart, there is the ball, and I have compressed the spring, and it is held by a pin below. So when I pull a string, which releases the spring, the ball will be shot up. Let's get over to this table and take a look at it. I'll put something down out of the way here. Let us take a look at it. Watch now, watch. I am going to drive the car away. So, pull the pin, up goes the ball, the car keeps going, and zowie, the ball is caught by the car. Watch it now. There it is. Now, I did not go so very high, and perhaps I should do that again to show you what a wonderful thing it is to witness. Watch it. Watch it. Oh, this is... There it is. And I say, this is enchanting to witness, which suggests a very important piece of physics. The horizontal motion of the car, which we would refer to as V horizontal, the horizontal velocity, is independent of the vertical velocity. Each goes its own way without interference by the other. Now, here is an experiment that I wish to talk about, but will not show you, and I suggest you try to make the apparatus yourself. I call it the monkey and hunter. Here it is. Let us take a tube, say of lucite, such as I have here, and let us bore sight on a monkey here. That's why I call it a monkey and hunter. Now, what is the monkey going to be? The monkey is going to be a tin can held up by an electromagnet. Now what am I going to do? I'm going to put a light, say a lucite ball, in this place here, in the chamber of the gun, and I'm going to have two little wires across the end of this tube, such as I have right here. If you look carefully, I'll take that stopper out. Now, what happens? When these two wires are crossed, the electromagnetic circuit is closed and the tin can is held up. Now I put my mouth to this end in this fashion, and I blow. Now you know what happens. The projectile emerges here. As it emerges, it opens the two little wires. The electromagnet loses its magnetic hold, and the monkey falls down. There's the monkey. Now let's say the monkey falls to there in a certain time. And what do we expect? We expect the projectile to hit him. And here is a very important detail. The monkey can never be hit at that place if he stays there. Why? Because the moment the projectile emerges, it is taken down by gravitational forces and can never hit the monkey. That is to say, looking at it in another view, that if we had a gun aimed absolutely horizontally at a target on the nose, and we fired the gun absolutely horizontally, and the projectile emerged there, we could never hit the bullseye. Never. Why? Because the instant the projectile emerges, it is taken down like that. And as an illustration of numbers, supposing the muzzle velocity of the gun was 1,000 feet per second. 1,000 feet per second. Supposing this was 1,000 feet. and supposing under ideal conditions the horizontal velocity of the projectile remains unaltered, it would take 1 second for the projectile to reach the target. But in 1 second, how far do gravitational forces take the projectile? As we discovered, 16 feet. Now somebody says, look here, Professor, I shoot guns and I hit targets. Of course you do, because what is really done is this. The sight on the gun is such as to compensate for this fall due to gravitational forces, and so the projectile is hit. So, remember, it is Newton and Galileo, very important in the case of falling bodies and projectile motion. Now, here is another experiment that you can do. Did we not say that when a body falls from rest, it falls successively farther, and the distance is 16 feet, 48 feet, 80 feet, and so on? I have here another experiment that you can do, and we need to take a look at an apparatus which you can make at home. It consists of a string to which are attached some spheres, and I have used billiard balls. And now, since this is pretty high, I will show you that at the bottom, the separation is closer and farther apart as we get higher. So the picture I have drawn on the blackboard is turned upside down. Now, supposing we release the whole string of things from the very top, would not the successive impacts of these balls on the ground be in arithmetic progression? Every second, let us say, one would hit, or every certain part of a second, but the distances are clearly in geometric proportion, as you see from what I have done on the blackboard. Very exciting adventures. And I must say again, this business of 1, 3, 5, uncovered by Galileo, and remember, this distance is 16 feet in the first second, in the first 2 seconds, 64 feet, in the first 3 seconds, 144 feet, and I wish to point out again, because this is enchanting to follow, this number, if we divide by 16 is 1, if we divide by 16 is 4, if we divide by 16 is 9, and you see 1 is 1 squared, and 4 is 2 squared, and 9 is 3 squared. So to quote Galileo, the distances passed over by a falling body beginning at 0 time are in the ratio of the odd numbers beginning with 1, 1, 3, 5. But the total distances passed over, 16, 64, 144, are in the ratio of the integers beginning with 1 squared. 1 squared, 2 squared, 3 squared, and so the next must be, of course, 4 squared, and so on. And since I have spoken about Galileo, we should take a look at this wondrous gentleman of Florence and Pisa and Rome and Padua. And here is Galileo, 1564, 1642. And I thank you for attending to our business.